Thank you. Okay. Hello all and welcome. In today's talk, we'll be introducing the tool GOFinder AI. In a time where there is over 1 million articles getting published every single year in the field of biomedical sciences alone, biomedical researchers are having a tough time keeping up with the publications and the data that is relevant to their respective fields of interest. Now, GoFinder AI is a tool designed to keep researchers up to date with the functional insights relevant to their entities of interest that they are researching, whether that is a protein, a gene, a metabolite, etc. Now, traditionally, to learn more about the function of their entities of interest, researchers refer to the gene ontology database. Now, one of the downfalls of this database is its current over-reliance on manual curation and manual updating. And in a time where there are thousands of articles getting published daily, this approach of manual curation is simply incompatible. And so with GoFinder AI, we attempt to leverage large language models to digest and analyze this sheer amount of articles that are getting published daily and update the researchers with the most recent functional insights. Now, GoFinder AI follows an intuitive two-step process. The first step being extraction. So extracting the evidence from reputable sources of literature like NCBI, PubMed, that discuss your entity of interest, whether that is a protein or a gene, etc. And then from this extracted evidence, map using large language models the evidence to gene ontology terms. We chose the gene ontology terminology because it offers a standardized way of communicating functional insights to the researchers using our tool. Now, here is a simplified framework that we're going to use throughout the presentation to explain the tool. Now, pre-query interface, you're essentially providing us with the details relevant to your entity of interest, the gene name, the ID associated with the gene or the protein that you're researching. And then automatically the tool is extracting the most recent publications and lines from these publications that give insights into the function of your entity of interest, and then mapping them via LLMs to gene ontology terms alongside providing the reasoning. Now, let's start with the first step, which is the evidence extraction step. Extracting functional evidence from reliable sources of literature involves two key steps. First, upon providing GoFinder AI with the information regarding your biological entity of interest, the tool, using a built-in Python code feature known as NCBI extract, extracts publications from the NCBI PubMed database that discuss the biological entity of interest. Each of these publications then are fed in one by one into the model, and using a second-hand feature known as Smart Extract, the tool extracts lines or citations from each of these papers that discuss the function of the biological entity of interest. Smart Extract essentially is a zero-shot llama LLM that we leveraged to do that task, the digestion of the publication and extraction of lines that discuss the function of the biological entity of interest. Now that we have these functional citations, the second step that is, in my opinion, more interesting and complicated is the mapping step. Mapping functional citations to Go terms in a fashion that is reliable and explainable using large language models was a challenging feat. We encountered basically three key challenges. First, reproducibility. So large language models, even though we provided them with the same functional citations, tended to provide or give varying functional Go mappings. And one of our goals with GoFinder AI was to generate consistent Go mappings provided the input. Hallucinations was another challenge. Essentially, with such a biomedical heavy task, large language models tended to generate false annotations, and even worse, Go annotations based on falsified evidence. And so we wanted with GoFinder AI to minimize these hallucinations as much as possible as well. Thirdly, For each GoFinder mapping that it provides, we made sure that it provided also reasoning. This allowed us to assess the quality of the Go annotations logically. And so let's see how we addressed each of these challenges. First, for the challenge of reproducibility, we, over a number of iterations, optimized a prompt that, when used plus the functional citations, generated a structured, consistent output. Essentially, the output is as follows. We have the Go term, the text citation that was used to map that Go term alongside the reasoning, laid one by one. And another two features that we used to generate more consistent, reliable results were self-consistency, whereas the large language model ran 3 independent times, generating all sorts of Go mappings, and we only selected the Go mappings that were consistent across the 3 reruns. Another feature was RAG, Retrieval Augmented Generation. Essentially, the large language model, before it generated the final Go annotations, it double-checked its output with the gene ontology database, making sure that the Go term is not outdated, that it mapped, and also making sure that whatever Go mapping that it generates is the most specific to the functional citation that was provided. Now that we've in part addressed that issue of reproducibility, and also, as mentioned earlier, with interpretability, we asked the model to provide reasoning. Looking at the issue of hallucinations were the most challenging feat of them all in trying to minimize. Let's look into how we minimize them. To address the issue with hallucinations, which typically stems from the fact that large language models are typically not experts in biomedical sciences, and also are not particularly trained on manual curation. So what we did is that we extracted 8,750 examples from the Go database that has Go terms and publications. We added to these text citations and reasoning that support each of these annotations. We also, in addition to the true annotations that are provided in the Go database, added some false examples such that the large language model is trained on both true and false examples. Let's look at an example of these. So the trail protein, according to one of the publications, is a pro-apoptotic protein. So it makes sense that one of the true annotations manually curated was the positive regulation of apoptotic process. Now, one of the false annotations we assigned automatically via Python code was a hierarchically distant annotation by the name of positive regulation of RNA polymerase II transcription. This annotation has no relation whatsoever to the evidence provided at hand, so it is a false annotation that is statistically false. And using both these false and true annotations, we fine-tuned or further trained that the large language model, the DeepSeek model more specifically, on the examples. And looking at the loss curve, we see that it achieved over time, training time, an optimized learning process, in that it learned the patterns that we used or the patterns that were used in curating the Go term annotations to PubMed evidence. Looking at the results and the effect of the fine-tuning, the fine-tuned DeepSeek model, when tested over 1,000 examples, achieved higher accuracy results than both the closed source ChatGPT model and the zero-shot llama model, which is an open source model that has not been fine-tuned and just been used as is. And so, according to these results and looking at the metrics, we can see that the fine-tuning had significantly improved the accuracy results, but there is still a way to go to further minimize accuracy. Looking at the significance of the tool, we hope for this tool to be a beneficial tool for the researchers to stay up to date with the functional context of their biological entities of interest, and also act as an auto-curator of the Go database, the standard. Rather than relying on manual curation, we hope to leverage GoFinder AI to keep the database up to date with the latest literature and minimizing discrepancy between the recent results and the database. Future directions involve further fine-tuning. We have still larger data sets that we can further enhance the quality of the mappings that can be generated by the model. Also, see how the model performs against entities like metabolites. And lastly, once we open source the tool soon, we hope to incorporate the researcher feedback. The researcher, upon getting the Go terms, can either save the Go term and approve of it or reject it. And this human in the interaction or researcher interaction can be used to further enhance the LLM output. I'd like to thank my PI, Professor Arvind Mir, and the members of my lab for all of their help and support. I'd like to also acknowledge NSERC and the Stem Cell Network for funding this research, and thank GLBIO for organizing this amazing conference. Thank you so much, and until next time.
Awesome.
Thank you, Mr. Ahmad. That's wonderful. Anybody has any question? You want to come here?
You can use that one.
Yeah, that's fine.
That was fine. Yep.
Hello.
Okay.
Hi.
I was wondering, would it be better to use positive unlabeled learning because of the open world assumption? A protein without that Go term annotation is not negative because maybe in the future we'll figure out that protein has that function that you previously assigned as a negative annotation.
That's definitely a valid concern. Now, with the false annotations, the rationale was for us to be able to get results that are precision, like more than just an accuracy or test only on positive results. So that was essentially the motivation of trying to generate false examples as well. Now, in the false example, I tried to make sure that whatever Go annotation is assigned is as distant in terms of a Go hierarchy as possible. So yes, statistically, it is still possible for the this protein to actually have a relationship to the function that I assigned as false. But again, my attempt was to try and minimize that chance as much as possible. But your concern is indeed valid.
Thank you.
So you're pulling a lot of papers, thousands of papers, millions of papers. What happens when the functionality of your protein of interest is contradictory in several papers?
Indeed, and that's a great question. Thank you for asking that. So statistical overrepresentation is our answer to that. So it depends on the protein, and it's a case-by-case basis. But some proteins have, as you've mentioned, contradictory results. Now, we will present the tool presents all of the Go terms and the citations and the PubMed reference. However, when the Go term is repeated across a number of papers, the confidence in that Go term is indicated by the number of supporting publications. So as a researcher, you might see you can see the Go term and the number of citations and the number of publications supporting that Go term. So you might be more confident in the Go terms that are more supported with more recent and more accumulating pieces of evidence. But in our approach to it is trying to show all of the results, and at the end, it can be assessed further by the researcher that is looking at the functional insight. And from a database perspective, we are providing all of the available results, contradictory or not.